If we want to understand reaction rates, we're going to have to understand the rate of collisions in the system because molecules have to collide in order to react. In order to derive an expression for the number of collisions in a gas, let's imagine a gas consisting of red particles and green particles. The red particles have a diameter of d sub A, and the green particles have a diameter of d sub B. If we want to count the number of times a green molecule collides with a red molecule, we can do that by imagining a cylinder in our gas. This cylinder is going to have the diameter that is equal to dB plus dA. Furthermore, I will make the length of my cylinder equal to the distance traveled by my B molecule in 1 second. If I do this, then any red molecule with its center in the cylinder will collide with the B molecule as it moves the length of the cylinder. And so if I just count the number of red molecules in my cylinder, I will have counted the number of collisions with my B molecule in 1 second. Notice that the volume of my cylinder is equal to the cross-sectional area times the length of the cylinder. If we know the volume of the cylinder and the concentration of A molecules in the gas in moles per liter, then we can find the number of moles of A in the cylinder by multiplying the concentration times the volume. Remember that the number of A molecules in the cylinder is equal to the number of collisions that a B molecule has undergone with an A molecule, because B molecules will collide with every A molecule in the cylinder. The cross-sectional area of the cylinder is often denoted by sigma sub AB. This cross-sectional area is also known as the collisional cross-section. This name makes sense because this is the area occupied by the two molecules when they collide. So far, we have the number of collisions of one B molecule with all the A molecules in the gas in the units of moles. If we want the number of collisions of all B molecules with all A molecules in the gas, we'll need to multiply this by the number of B molecules in the gas. The number of B molecules per unit volume is Avogadro's number times the concentration of B. Since we're interested in the rate of collisions, or the number of collisions per unit time, if we divide by time, then we finally get our collision density. Notice that this collision density has units of moles per unit volume per second. Recall that the average relative velocity between molecules comes from the Maxwell-Boltzmann distribution and is given by the square root of 8 times the Boltzmann constant times temperature divided by pi times the reduced mass between the two molecules. Recall that the reduced mass is equal to the product of the masses times the sum divided by the sum of the masses. If both A and B are the same molecule, in other words, if we're looking at collisions between A molecules, then the reduced mass will be mass of A times the mass of A, so the mass of A squared, divided by the mass of A plus the mass of A, or 2 times the mass of A. So the mass of A squared divided by twice the mass of A is equal to the mass of A divided by 2. Thus, the relative velocity between two identical particles is equal to the square root of 2 times the relative velocity between dissimilar molecules. Therefore, the collision density between similar molecules is given by Avogadro's number times the concentration squared times the cross-section times the relative velocity divided by the square root of 2.